So I'm here to talk about Lustre, the file system, and I'm just going to spend a couple of minutes telling you about Whamcloud, who we are, and why we exist, and what we do. And then most of what I'm going to be talking about is a roadmap for Lustre, which is really the work that's ongoing and the work that's planned, and the work we'd like to do to keep Lustre developing. I also want to talk about how we grow the Lustre market, because it's there's no sense in having this nice little niche in HPC when the technology is much more widely applicable. And with wider applicability will come great benefits, I think, for the HPC community. And then looking ahead towards some of the challenges for Exascale, John Barr mentioned this morning that there are some major scary issues waiting for us, especially in the hardware. I'm kind of ignoring some of the hardware issues, assuming that there is going to be some sort of a viable storage technology coming up. And really, what do we have to do with the software to make it, to be able to exploit it? Okay, so to begin with, what is Whamcloud? Well, really, Whamcloud is really the Lustre engineers. I mean, we've been working on this thing since the early 2000s, and it's fundamentally the same group of people. We were working in a company called Cluster File Systems originally, which was acquired by Sun. Sun in turn was acquired by Oracle. And it was sometime during that it became clear to some of us working inside the group of Lustre engineers that if you like, the direction for Lustre was being sidetracked. And we were very keen to ensure that it continued to be a vendor-neutral technology. And so, well, this kind of came to a head, I guess, 2 years ago at the Lustre User Group, when some of the things that had been sort of going on underneath the surface finally came out, and Oracle announced that there would be restrictions on the configurations of Lustre they would support and so on. And about a year ago, that was when Whamcloud started up, and our fundamental purpose is to continue to develop Lustre, not just for any single vendor, not just for any particular special interest group, but actually on behalf of the whole community. And so one of the things we're very pleased to be able to say is that we are multi-vendor. We have partnerships with several different storage vendors, notably DDN and well, what used to be LSI and is now the HPC storage group inside NetApp. And we've been working with Bull and various other partners. So we continue to support the Lustre community, and the way we do that is by working with the community groups, most notably OpenSFS and the European Open File Systems Consortium. And we worked really hard, actually, to make sure that HPCFS and OpenSFS could eventually see eye to eye, bury their differences, and get together. And that happened around about the Lustre User Group this year. So one of the changes that we made to the way that we work is that now that we're outside of Oracle, and we can provide a community, a set of community repositories. We've dropped any sort of IP requirements on contributions. This was something that Oracle insisted on, so that they could use whatever IP was contributed in any way they saw fit. We personally see the fact that the pool of IP inside Lustre is effectively polluted. In other words, everybody's IP is intermingled, means that it will safeguard the future of Lustre, because then no single entity can then start saying, well, that's my intellectual property and I want to use it in this way and you can't have it. So the removal of copyright assignment on contributions, I think, is key to continuing the contributions from the community. And we offer various community resources. They're all listed here for development and collaboration on test and producing releases. So, what's the current status of Lustre? Well, we're in the middle right now of helping to produce Lustre 2.1, and we're also imminently about to release a Lustre 1.8. Now, why are we doing two sets of releases? Well, really, we want to have two different streams of effort. There's one stream in which advanced development is happening, and we're making new features come available as soon as possible so people can try them out. And then there's the other stream, which is for people that are deploying Lustre in production environments, and their stability has got to be the most important thing. If there's one thing we learned over the years, it's not to mix features into stable releases. You just piss off a lot of people doing that. And so we're formalizing, if you like, a maintenance stream and a feature stream. And the current maintenance stream is Lustre 1.8. It's extensively tested. We're not adding any major new features. And then Lustre 2 is the feature release, and that's the version of Lustre in which we've re-architected some of the internals, and we're busy implementing new features. So, if you go to the Whamcloud wiki, the roadmap is up there, and it shows you exactly this picture here. It's two streams, the maintenance release along the top. We're aiming for, sort of a 6-month, 4-month, whatever, however quickly we can incorporate fixes. We'll be producing to a regular cadence. But obviously, Lustre 2 is where the interest is right now. We spent 3 years really inside Sun and then Oracle stabilizing the code base that was originally developed for the clustered metadata project with Livermore. We've continued working on stability of that over this last year. And Lustre 2.1 represents the next increment of functionality and stability for Lustre 2. We'll continue to make developments on it, and in this diagram here you can see that along the 2.1 line there are these boxes with some features listed. The reason we can list them there and not there on the right where it says future features is because this is all work that we've not only done some of the preliminary design for, but we've actually sized the amount of work that's required. That's why we think we can predict with reasonable accuracy when releases containing these features might be present. So that includes, for example, on the right there, you can see some stuff in red underneath OSD restructuring. That's work that we've actually sized for quotation to the OpenSFS. And so if OpenSFS awards us the contract to develop it, that's when we think we can deliver it. And there are all these other desirable features here on the right. These are all features which we may have done some work on thinking about, but we don't have a strong enough plan for them to be able to give you with any reliability a release date. And so that just keeps there on the right. What we're hoping then is that as time progresses and as funding becomes available, we can take these features there on the right and start to plan them in more detail and give them actual release dates. So the next releases of Lustre 1.8.6. Now Oracle just produced a 1.8.6 release, and we actually think it was a little premature because there's one feature that everyone, or rather one limit that everyone's running into, which is the 16 terabyte LUN limit, which with 2 terabyte disks isn't so bad. With a RAID 6 set of 8 plus 2, that gives you a 16 terabyte LUN. With 3 terabyte disks though, 8 plus 2 goes over the limit, gets you to a 24 terabyte LUN, and that's been an issue for Lustre. We've been working on that. We're actually hoping that people in the community would come forward with some funding for it. It wasn't available, so we just carried on with that and did the work ourselves, because we think it was it would become a major barrier to adoption of Lustre. And so this feature of large LUN support, we're testing up to 24 terabytes for the 1.8.6 release, and that will be available by the end of this month. In Lustre 2.1, we'll be continuing that testing. In fact, the work we've done removes the limit altogether on LUN size, but because we actually have to test the damn thing in case of surprises, that's why we're not saying we will guarantee more than 24 terabytes for 1.8.6, but for 2.1 we're hoping to have proved out all the way up to 128 terabytes, which should keep us out of trouble for a while. In 2.1 we'll also be turning on async journal commits, so that means that we are much less dependent on SSD, fast SSD storage for journals, for example, in order to get high throughput rates. And ext4 LDiskFS enabled by default as well. So those are the immediate upcoming releases. The next two boxes, LNet SMP scaling. That's something that we'd like to get into a release before the end of the year. In fact, work on LNet SMP scaling has been in progress for the last 2 years. So there's a patch set waiting to land, and we keep putting off landing it because we don't want to destabilize the feature release too much. But after 2.1 gets out, I think we'll have some time to be able to work on landing it and testing it properly. Just to give you an idea for the performance boost it can give you, prior to the work on LNet SMP scaling, we were seeing something like a 30,000 ping rate, independent of how large a node, like a metadata server, for example. It's all small messages, and so the ping performance, the ping throughput is key. We're seeing something like 30,000 pings per second. With the SMP scaling work, we actually managed to get on I think it was a 16-core SMP, we're getting like 1 million per second. So it's a huge performance increase for the messaging. Unfortunately, as you must all be aware, in scalability, lose it anywhere, you've lost it altogether. And so LNet SMP scaling is just the beginning, really, of the SMP scaling work. We need to keep on progressing that work down the server-side stack, and I'll be talking about that in a minute. Yeah.
How much scaling in messaging will be affecting the scaling in metadata part?
So fundamentally, a metadata server should really, what should it be doing? It should be working on, everything should really be cached, and updates should be streaming through the logs to disk. And so really, CPU is a major bottleneck for vertically scaling metadata. And so all the work that we can do on SMP scaling is going to have immediate benefit in terms of aggregate throughput achieved for on metadata for the whole cluster. Does that answer your question? Okay, so I'm just going to talk about work, a couple of projects that are underway right now. We're being somewhat conservative about when we think this work can land. It's just our experience that it takes sort of 6 months of landing effort, sometimes longer, in order to get something which has looked very strong, in the prototype stage, has survived initial testing, but then you start subjecting it to the full rigors of the configuration matrix, and you start discovering holes in it. And of course, with a crucial resource like a file system, you have to do this testing. And so it's really unrealistic to expect features that are in development right now to land in under 6 months, and 6 months to a year is much more realistic estimate. Okay, so this is some work that we're doing in conjunction with Oak Ridge, and the object of the exercise is to accelerate directory traversal, ls-l for interactive users. We're trying to get that to go faster. So single client performance, it's the path across the network, through the server stack and back again that we need to get fast. Now the reason it's slow is fundamentally because of the way we sequence RPCs. We're only got one RPC on the wire at a time to the metadata server when you're doing LS. And that means that every single file you touch, you've got a network latency in the way of it. That stacks up, and that results in tens of seconds to list a reasonable sized directory. So the work we've done is to pipeline this these RPCs so that we read directories in larger chunks. We stat the files in directories more continuously. And a big part of statting a file is knowing its size, and the size is derived from the stripes of the file. If we were to keep the size up to date at all times on the MDS, then every time you wrote somewhere, you'd also have some MDS traffic. That's just not scalable. So the compromise is you let the size be unknown until you need to know it, and then you calculate it. Now, even if we were to cache the size on the metadata server, the SOM, we'd still be in this issue for files that have been modified. And so this performance improvement here is of general benefit. You go and touch everything in a directory, and then ls-l it or du it. This will give you the performance benefit. So here's some figures that show what sort of performance we've achieved. Notice that these are log-log graphs. And so on the left-hand side, this is just the improvement that we've made to the basic communication with the MDS. That's a factor of 4 or so. But the win starts to become more apparent when we look at files with stripes, where we have to calculate the size as well. And there, because we're now properly pipelining the stat RPCs to the OSTs, then we're able to get much improved performance. I mean, factors of, well, way over 10, which improve as you increase the size of the directories that are being statted like this. Now, this is work, once again, let me emphasize, this is work that's been done on a small test cluster. We still have to prove this out at scale. But you can see that there are great efficiencies to be had. So the other piece of work we're doing with Oak Ridge right now is to improve failover times. The project's called Imperative Recovery. So why do we need imperative recovery? Well, basically because Lustre fault detection at the moment is all based on timeouts. So the client sends an RPC to the server to do anything, waits for the result. If the server hasn't replied within a certain time, then the client begins to think that the server might be dead. That sounds great until you realize that for some I/O patterns that applications will do, you get a huge amount of convergence on a single server. In other words, the server gets congested. Now, when a server gets congested like that, if the service queue depth gets to be hundreds of thousands of items, and in a large cluster like Jaguar, you'll see this, then the request latency just goes through the roof. Now, if you're basing your death detection basically on service request latency, that means that your timeouts to prevent you thinking that the server is dead have to become enormous. Now, when you're recovering a server, you have to have a window, a recovery window, when the clients are given a chance to reconnect to the recovered server so that it can restore its state back to what the state the server was in just before it crashed, before it starts serving new requests. So the reason for that is that you don't want the new requests to invalidate the recovery process. This is all about, because the Lustre protocol exploits caching on the server, it achieves much better throughput by pipelining. But of course, if you crash and the server has got a bunch of unsynced state, it has to be recovered. So, the current state in Lustre 2 and Lustre 1.8 is that when the server crashes, it has to give all of the clients time to time out, to cotton onto the fact that the server has crashed, and then try to reconnect. That's why the recovery times can be on the order of many minutes. And that's clearly not acceptable in a large production environment. However, we have this nice big network there. I mean, it might be congested on the way towards the servers, but it isn't generally congested on the way back to the clients. So if we could deliver notifications to the clients that actually the server is restarted, then we could actually reduce the recovery time. And that's exactly what imperative recovery does. So when the failed over servers restart, their targets notify the management server in Lustre. Now the management server can then deliver notifications to all of the clients. This is using the standard Lustre cache coherency protocol. So basically there's this table called the target NID table, which all the clients are going to cache, and to protect their caches they have a lock on it. So when the targets are trying to change this table by registering their new addresses, they enqueue an exclusive lock because they need to make a table change, so that delivers a notification to the clients. The clients can then cancel and re-enqueue their locks. The servers at that point, so the restarted servers at that point acquire their exclusive locks. I mean, this is a process that's occurring locally in the MGS. The targets are just requesting that they re-register. So, which means that we can, if we restart the whole machine, then the whole machine just goes through one cycle of this, not n of them. So when the change has been made in the target table, because the targets have all registered, then the clients can reacquire their locks and read the updates to the table. In the limit, this could be the whole table. But at that point, after they've read the table, they can reconnect directly to the targets. So there's no waiting. Everything latency of this whole process is determined by network latency, not by how long I might have to wait in case somebody's still wondering whether something's happened somewhere else and hasn't received a notification. So this has the potential to reduce failover times from tens of minutes down to tens of seconds. So there they are in our current vision of the roadmap. Lustre 2.3 is probably when these developments for Oak Ridge could be landed. At the moment, this project is going very well. We have very strict project management controls in place, and at the moment we are executing to plan. And so there's a possibility we could get some of that functionality into an earlier release. The other major project that's underway right now is this one, OSD restructuring. It's a very small name for a very big project. It's basically re-architecting the metadata server to use the same Lustre 2.0 stack as the it's changing the OSS stack to use the same stack as the MDS, basically, so that they can all utilize the same underlying storage abstraction. This is the OSD, the object storage device. What that means is that we can now, that would allow us to change the back-end storage implementation underneath Lustre, so that at the moment LDISCFS is your only choice, and it's accessed in two different ways. By doing this restructuring, then we can, for example, have a Btrfs OSD. Livermore have funded this work, and they're interested in it because they are implementing a ZFS OSD. So, metadata performance. We think there are two ways to improve metadata performance. I talked earlier a little bit about SMP scaling, which means you can squeeze more out of a single server. And this is some work, preliminary experimental results that we did that show, on the left here is the SMP scaling work that shows that we can keep on scaling file creates per second as we increase the logical client count. On the right, you can see we're blocking off at about 30,000 per second there. The other way to increase, and the truly scalable way to increase metadata throughput, is just to employ more metadata servers. And we're calling this distributed namespace, really partly, I guess, to get away from the previous project that didn't implement this so successfully, but also because we're approaching this in a different way. In the first phase, all that we will be doing is distributing the namespace. The idea behind this whole project is that the system administrator can use distributed operations to create a scalable namespace, and then regular users just do normal operations on it, which are always local to their own metadata server, but they get the benefits of scaling that way. In the first phase, we'll be just moving whole directories onto separate nodes. In the second phase, we'll be striping directories across multiple nodes, so that when we're creating multiple files all in the same directory, then those file creates will hash over all the metadata servers that the directory is striped over, and therefore we will trivially achieve an order n speed up. So we think that that really is the right way to keep Lustre, to allow Lustre to carry on being scalable. At some point, SMP nodes, SMP scaling on a single node is going to run out of steam, or the cost performance of the node is going to become unfavorable. That's why we think horizontal scale is essential. So one other thing, I'm afraid I'm going to have to skip on a bunch of this presentation, but one thing I do want to talk about is growing the Lustre market. And there are two major barriers, I think. First of all, it's administration. At the moment, administrating a Lustre file system is a nightmare. And anything that can simplify that. I mean, obviously a GUI where you can point and click and just do intuitive things is a nice way to go. But you know, real system administrators also want to be able to script their administrative procedures. And so we are designing a new piece of administrative infrastructure for Lustre. The project internally is called Hydra, and it's really it's architected so that it really understands the administration process for Lustre. I mean, yes, it can interface to a GUI, but actually it can also, it's being designed to interface to vendor site management systems, so that it's not just some separate some separate screen that you have to go to when you want to do something on the file system. It can be right there, right in the middle of your site management system. Similarly, that's looking up. Looking down, we need to integrate with a number of different vendors' hardware systems. And so the whole purpose of this is to give you one system that can adapt across multiple vendors and be used in all different sorts of ways. The other side to this, and we've talked about this before, is stability. It's ensuring that the releases that we produce are stable and can be relied upon when you go into production. That's why we're being very strict about separating out the maintenance and feature release streams. That's why we're putting a lot of effort not only into our design and implementation process, but also into our test infrastructure, so that it can be deployed by other people, and a whole community can share their test results and benefit from the testing done anywhere. So I'm afraid I'm going to have to skip on the Exascale challenges. I think there's lots of interesting work to be done on Lustre as we approach Exascale, mainly to avoid the fundamental serialization issues that POSIX gives you, and to give you a much more flexible I/O model. But if anybody wants to talk to me about that, I'd be very happy to chat. Any quick questions?